Welcome to the first of many correction videos. Throughout the recordings for these videos, you're likely to hear all kinds of background noises. Meowing, purring, the crying of a 4-year-old. I apologise in advance and hope that you can understand them and they allow you to learn from your mistakes regardless. These are the corrections for IB Measurements 1.1 test. Questions 1 and 2 are fairly straightforward. They require you to learn off by heart the 7 fundamental units: time, temperature, current, etc. So just by learning those 7, you should be able to recall that from this list, the Newton, the Coulomb, the Ampere and the Joule, the Ampere is the only one that's in that list. Go back to your booklet, the first lesson, where you wrote down the 7 units. And some of you came up with some really cool ways of remembering them too. Question number 2 is virtually the same. Here you have to find a fundamental and a derived unit. So if you have a look at each option, we have the first where you have a fundamental unit, but also another fundamental unit, the second. The Coulomb is a derived unit, and the kilogram is a base unit, or a fundamental unit. C, the Coulomb is derived, but the Newton is derived as well. And in D, we have a fundamental and another fundamental. So the only one that would give you the answer of a fundamental and a derived is B. Question 3. What are the units for momentum if momentum is equal to mass times velocity? You build the units for momentum by using the units for mass, which are kilograms, and velocity, which are meters per second. So the base units would be mass, kilograms, times velocity, meters per second. That's worth 1 mark. Torque is now force times distance. So if we have to build the units of torque, what we need are the units of force times the units of distance. The units of distance are meters. The units of force are kilograms, meters second squared. So if we now put those together, we have here force, which is kilograms per meter second squared, times distance, which is meters. If we simplify, we have kilograms, meters squared, because it's meters times meters, to the power of s to the minus 2. Question 4 requires you to express the following in scientific notation to 3 significant figures. So let's have a look at the data. Scientific notation means that you have to express this number firstly as a number between 1 and 10, so that would be 4.5678, but times 10 to the power of 4. How do we know? Well, if I bring this over 1 step, 2 steps, 3 steps, 4 steps. So it's 4.5678 times 10 to the 4. However, we need it to 3 significant figures. So we're left with 4, 5 and 6. That would give us 3 significant figures. But as you can see, the 7 is greater than 5. So really you should be rounding the 6 up to a 7. Quite a few of you haven't done this, and that's why you've lost 1 of the 2 marks in this part of the question. Similarly, 5, our beginning or our start of scientific notation would be from 1 to 10. So we're looking at 5.6789. That's what this number needs to look like. But in order to provide that format, how many noughts do we have? 1, 2, 3, 4, 5, 6, 7 and 8. So this number is equivalent to 5.68 times 10 to the power of 8 minus. Now what happens? We've got 3 significant figures, 1, 2 and 3. So this number must round up to an 8 because this number is greater than 5. I'm a little bit concerned by your lack of rounding up generally, so we'll have to talk about this in class. The next question is about significant figures. You're multiplying two numbers and applying the following rule. The number of significant figures has to be equal to the smallest number of significant figures in the question. So here we have 56.2, which is 3 significant figures, and here we have 0.42. So we have a minimum of 2 significant figures. So when you multiply these two, you should get 23 point something, but it rounds up to 24, which is 2 significant figures. 543 times 0.2, you're going to kick yourselves. A lot of you wrote 108, but if you round 108 up to 2 significant figures, it's 110. So that's the only mistake that some of you made. The next question. We have two numbers in a calculation, 12.2, which is the voltage, times 0.2 amps. Now, you're going to calculate those two together as it states here in the formula, in the equation, current times voltage. But what you're required to do is give your answer to the correct number of significant figures. Now, I've been generous with this because you haven't fully been told why this is definitely 2 significant figures and not 1. It could be 1 numerically, because it could be that this is just given to 1 significant figure. But you'll understand in the new topic when we talk about instrumentation why this is definitely 2. Now, where am I going with this? If you assume that this is the smallest, that this is 1 significant figure, then A would be correct. If you've assumed that 2 is the smallest amount of significant figures, then B is correct. And I've accepted both of those answers. It can't be these two, because these are 3 significant figures. And so, why do we know that? Because the smallest amount of significant figures is the rule that you must apply. Okay, question 7. This is a bit of a trick question, because basically what it's asking you is what the SI units actually are for this situation. The SI units, or the fundamental units for time, are seconds. So you either know this or you don't. The answer must be C, because it's giving you the answer in the appropriate units. I think everybody got this right though. Question 8. First mistake is this should be a 3. This question is out of 3 marks. 6A. Calculate or give the order of magnitude for the following measurements. An order of magnitude is an expression to the power of. Now, this stage, I'm going to just quickly correct my mistake, because this should be 10 to the 7, and I'll tell you why in a minute. Okay, so the first thing you have to do is decide what, basically you have to convert this into scientific notation. So we need to go from 6.3 or 6.37, but how do we express it in that form? Well, you need to count the number of decimal places. So it'd be 1, 2, 3, 4, 5, 6. 6.37 times 10 to the 6. Now, this is a bit of a tricky one, because if it was 5 times 10 to the 6, or even just a little bit more, let's do 4.9 times 10 to the 6, then the order number would be 10 to the 6. But this is actually closer to 10,000 than it is to 100,000. So you round it up to the greatest significant figure. So this should be 10 to the 6, but it's actually 10 to the 7 because this value is closer to 10 than 1. B. The half-life of a radioactive isotope is 0.0015 seconds. So if we place this, or we write this in scientific notation, we have 1.5 times 10 to the 1, 2, 3. And that actually stays the way it is, 10 to the minus 3. The mass of Jupiter, well, you count all these. If we put this in scientific notation, here in 1.87, we would go 3, 6, 9, 12, 15, 18, 21, 24, and 27. And it's closer to 1 than it is to 10, so it's 10 to the 27. Question 9. Meters to centimetre conversion. The first thing to do with this question is to ignore the squared and just see how would you express 2 meters in centimetres. 2 meters in centimetres would be 2 times 10 to the 2. That gives you your answer in centimetres. But now we want centimetres squared. So all we do is just square that transition to 10 to the 4, which gives us B. And then question 10 was pretty straightforward. Giga, you could look up on the page, the data booklet. Giga stands for giant, by the way. So you should have seen that's equivalent to 10 to the 9. And we have here 3, 6, 9 placements. Okay, so I hope that's a little bit clearer now.